Now in this lecture I'll answer two questions. In the first question you find out the radius of this circle, and in the second question you find out the area of this green shape. So we start with the first question. In the drawing we have quadrilateral ABCD that is described by this circle. Side AD of this quadrilateral ABCD equals to 6 units in its length. Side DC equals to 5 units in its length. Side BC equals to 4 units in its length. And side BA equals to 3 units in its length. Again, our task is to find out the radius of this circle. So first of all, we define this angle BCD is alpha. Okay, again, we define this angle BCD as alpha. This is the opposite angle of alpha. The opposite angle of alpha, this angle BAD must be equal to 180 degrees minus alpha. According to rule 22. Repeat again. Rule 22. According to rule 22, the sum of two opposite angles in a cyclic quadrilateral is equal to 180 degrees. Quadrilateral ABCD is of course a cyclic quadrilateral, therefore the sum of those two opposite angles must be equal to 180 degrees. That is to say, A plus B equals to 180 degrees. Likewise, the sum of those two opposite angles must be also equal to 180 degrees. That is to say, x plus y equals to 180 degrees. So, in the cyclic quadrilateral ABCD, the sum of those two opposite angles must be equal to 180 degrees. This is angle BCD, is equal to alpha according to our definition. Therefore, the opposite angle must be equal to 180 degrees minus alpha. Because 180 degrees minus alpha plus alpha is equal to 180 degrees. That is the sum of those two opposite angles inside the cyclic quadrilateral ABCD according to rule 22. Therefore, this means the angle must be equal to 180 degrees minus alpha. In the next step, we join points B and D together by straight line. By joining points B and D, we divided quadrilateral ABCD into two parts. The first part is the upper green triangle, triangle ABD. And the second part, again, the first part is the upper triangle ABD, and the second part is the lower triangle, triangle BCD. So in the next step, we will implement the law of cosines on both triangles, on the triangle ABD and on the lower triangle BCD. So repeat quickly on the law of cosines. The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. This is angle BAC, equals to 30 degrees in size. This is side AB of triangle ABC. This is equals to 80 in size. This is side AC. This is equals to BB sensor, finally this is line BC, of target ABC, this is equals to service in its length. So in this target ABC, that could be any target according to the law of cosines. The following equation is to C square equals to A square plus B square minus 2 times A times B times cosine theta. Again, C square equals to A square plus B square minus 2 times A times B times cosine theta. So the first step, we implement the law of cosines of this given triangle ABD. So according to the law of cosines, in this given triangle ABD, the following equation is true. BD square equals to AD square plus AB square minus 2 times AD times AB times cosine 180 degrees minus alpha. And again, in this given triangle ABD, according to the law of cosines, the following equation is true. BD square equals to AD square plus AB square minus 2 times AD times AB times cosine 180 degrees minus alpha. This is equation 1. Equation 1 is the implementation of the law of cosines on this given triangle ABD. We have the trigonometric identity that says that cosine 180 degrees minus alpha equals to minus cosine alpha. So according to this trigonometric identity, we get that cosine 180 degrees minus alpha equals to minus cosine alpha. So in total we have, according to equation 1, BD square equals to AD square. And again, BD square equals to AD square. AD is 6, therefore AD square is 6 squared, it is 36. Plus AB squared. AB is 3, therefore AB squared is 3 squared, it is 9. Minus 2 times AD is 6, times AB is 3, times cosine 180 degrees minus alpha. And cosine 180 degrees minus alpha according to this trigonometric identity equals to minus cosine alpha. So this expression in the green color, we have minus times minus, that is plus. So total, this expression is a positive expression. The value of this positive expression equals to plus 2 times 6 is 12, 12 times 3 is 36. So total, this expression equals to 36 times cosine alpha. This expression in the green color equals to 36 plus 36 times cosine alpha. Well, here we have also 36 plus 9 is 45. So total, according to equation 1, if you found out that BD square equals to 45 plus 36 times cosine alpha. This is according to equation 1. So in the next step, we will implement the law of cosines in this lower triangle, BDC. So in the lower triangle, BDC, according to the law of cosines, the following equation is true. BD square equals to DC square plus BC square minus 2 times DC times BC times cosine alpha. But again, this lower triangle BDC, according to the law of cosines, the following equation is true. BD square equals to DC square plus BC square. And again, BD square equals to DC square plus BC square minus 2 times DC times BC times cosine alpha. BD is the missing side, so here it is. Get that BD square according to equation 2 equals to DC square. DC is 5, therefore DC square is 5 squared, that is 25. Plus BC square. BC is 4, therefore BC square is 4 squared, that is 16. Minus 2 times DC is 5 times BC is 4 times cosine alpha. So total, according to equation 2, if you found out that BD square equals to 25 plus 16 is 41. And we have minus 2 times 5 is minus 10, and minus 10 times 4 is minus 40, so this expression in total equals to minus 40 times cosine alpha. So according to equation 2, if you found out that BD squared equals to 41 minus 40 times cosine alpha. This is according to equation 2. But according to equation 1, we only found out that BD squared equals to 45 plus 36 times cosine alpha. Repeat again, according to equation 1, we only found out that BD squared equals to 45 plus 36 times cosine alpha. So we have two equations, two different equations for BD squared. Equation 1 and equation 2. Therefore, we get equation 3. It says that BD squared according to equation 1 must be equal to BD squared according to equation 2. Very simple equation. BD squared according to equation 1 equals to 45 plus 36 times cosine alpha. And it must be equal to BD squared according to equation 2. BD squared according to equation 2 equals to 41 minus 40 times cosine alpha. So according to equation 3, we found out that 45 times 36 times cosine alpha equals to 41 minus 40 times cosine alpha. Here we will subtract 41 from this equation 3. So here 41 gets cancelled. This side of equation 3 we have only with minus 40 times cosine alpha. And on the other side of this equation 3 we have 45 minus 41 is 4 plus 36 times cosine alpha. So in total according to equation 3 we found out that 4 plus 36 times cosine alpha equals to minus 40 times cosine alpha. So here we add 40 times cosine alpha to this equation 3. So 40 times cosine alpha minus 40 times cosine alpha equals to 0. So here we have to nothing, that is to say 0, and on the other side of this equation 3 we have 4 and 36 cosine alpha plus 40 times cosine alpha equals to 76 cosine alpha. So in total according to equation 3 we found out that 4 plus 76 cosine alpha equals to 0. Here we subtract 4 from this equation 3. So on this side of the equation 3 we have 4 minus 4 is 0, so we left only with 76 cosine alpha. And on the other side of this equation 3 we have 0 minus 4 is minus 4. So in total according to equation 3 we found out that 76 times cosine alpha equals to minus 4. So here we divide this equation 3 by 76. Again according to equation 3, 76 cosine alpha over 76 equals to cosine alpha equals to minus 4 over 76. So in total we found out that according to equation 3, cosine alpha equals to minus 4 over 76. We would like to find out the value of angle alpha itself. In order to find out the value of angle alpha itself, we have to operate the opposite function of cosine on the result of cosine alpha. This is actually minus 4 over 76. In this way we get the value of alpha itself. So in the information for inverse, so the inverse function of cosine, we operate it on the result of cosine alpha. This is actually minus 4 over 76. And the result is angle alpha itself. So again, if you operate the inverse function of cosine, or the result of cosine alpha, this is minus 4 over 76, we get the value of alpha itself. You can find out in any simple scientific calculator that if we operate the inverse fraction of cosine on minus 4 over 76, the result will be 93.017 degrees. So again, the inverse fraction of cosine of minus 4 over 76 equals to 93.017 degrees. Those two sides of the equation are equal to each other. That is to say, alpha equals to 93.017 degrees in its size. So fundamentally, this is the angle alpha. This is equal to 93.07 degrees in its size. Write it down. Angle alpha equals to 93.07 degrees in its size. What is the value of BD? According to equation 2, we already found out that BD squared equals to 41 minus 40 times cosine alpha. But again, according to equation 2, we already found out that BD squared equals to 41 minus 40 times cosine alpha. So BD squared, according to equation 2, BD squared equals to 41 minus 40 times cosine alpha. And alpha is 93.07 degrees. So in total, if you found out that BD squared, according to equation 2, BD squared equals to 41 minus 40 times cosine 93.07 degrees. Actually, the value of this expression in the green color, in total, it is 2.105. So this plus 2.105. So in total, we found out that BD squared according to equation 2, BD squared in total equals to 41 plus 205 equals to 43.105. And again, in total, we found out that BD squared equals to 43.105. So here we take a look out of this equation. If I get that BD, the length of BD, the length of chord BD is equal to the square root of 43.105, that equals to 6.565 minutes in its length. So this is called BD. This is equal to 6.565 minutes in its length. In the next step, we will implement the law of sines in its full version on this lower triangle, triangle BDC. So please click on the law of sines. According to, first of all, the law of sines is true in any triangle. This is triangle ABC that could be any triangle. This is triangle BAC, this is equal to capital A degrees inside. This is angle ACB, this is equal to capital B degrees inside. that is equal to capital C degrees in size, and find this angle ABC is equal to capital B degrees in size. Likewise, side AB of this triangle ABC equals side AB of this triangle ABC equals to 70 in length, side AC equals to B units in length, and finally side BC equals to M units in length. In addition, we know that triangle ABC is inscribed by this circle. This circle blocks triangle ABC. We know that the radius of this circle is R. So the law of our drawing, again that according to the law of size in its full version, the following equation is true. A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. And now is the radius of this circle that blocks triangle ABC. So repeat again, according to the law of size in its full version, in our drawing, the following equation is true. A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. And now is the radius of this circle that blocks triangle ABC. So we can implement the law of size in its full version in our triangle BDC. Why can we implement the law of size in its full version? Because of the fact that triangle BDC is inscribed by this circle. Why triangle BDC is inscribed by this circle? Because of the fact that all the three vertices of triangle BDC, that is to say vertex D, vertex B, and vertex C, are located on the circle itself. The whole triangle BDC is inscribed by this circle. Therefore, we can implement the law of size in its full version on triangle BDC. So according to the law of size in its full version, in triangle BDC, we get that BD over sinus alpha equals to 2R. Again, BD over sinus alpha equals to 2R. Again, we implement the law of size in its full version on the lower triangle BDC. We get that according to the law of size in its full version, the following equation is true. BD over sinus alpha equals to 2R, and R is the radius of this circle that blocks triangle ABC. R is also the radius that we are looking for in this question. BD equals to 6.565 or sinus alpha. So it is sinus alpha is 93.07 degrees. Equals to 2R. So in total, according to the law of size in the solution, from order 3, that 6.565 over sinus 93.017 degrees equals to 2R. Actually, the value of this expression in the green color is equal to 6.5745. Those two sides of the equation are equal to each other. That is to say 6.5745 equals to 2R. Here we divide this equation by 2 and finally get that R, that is the radius of the circle that we are looking for, is equal to 6.575 over 2. 6.575745 over 2 is equal to 3.287 units in its length. But again, to know that the radius of this circle, that is the radius that we are looking for in this question, is equal to 3.287 units in its length. So we finish the answer on the first question. In the next step, I present you the second question, and answer the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have the big quadrilateral ABCD. Those three angles are right angles. Side AD of this big quadrilateral ABCD equals to 9 units in its length, side DC equals to 8 units in its length, and finally side BC equals to 7 units in its length. But again, our task is to find out the area of this green shape. So first of all, side AB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. So if you focus on the lower side of the straight line AB at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line AB at point B? We have this angle, that is the right angle, plus this missing angle, so the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we'll join points A and Q together by straight line. Likewise, we'll join points B and Q together by straight line. By doing those constructions, we can identify those two right angles. We have the right angle APQ and the green right angle PBQ. So in the next step, we prove that those two right angles can go into each other according to side against side rule. It is given us the question that AP equals to PB. Again, according to what is given in the question, side AP equals to side PB. So our task is to find out that to prove that the green right angle APQ can go into this. The task is to find out that to prove that the white right angle APQ can go into the green right angle PBQ according to side against side rule. So why those two right angles can go into each other? First of all, according to what is given is the question, side AP of the right angle equals to side PB of the green triangle. Repeat again. Side AP of the right triangle equals to side PB of the green triangle. In addition, those two angles are both right angles and therefore they are equal to each other. So here this is angle APQ of the right angle APQ and is equal to this angle, the angle BPQ of the green triangle PBQ. Repeat again. Angle APQ of the right triangle equals to angle BPQ of the green triangle. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side PQ. This is a common side that belongs to both triangles. So you can write down that PQ equals to itself is a common side that belongs to both triangles. Again, PQ equals to itself is a common side that belongs to both triangles. Therefore, those two right triangles can go into each other according to sine and side rule. So, the right triangle APQ congruent, this is the sine of congruent, to the green triangle PBQ according to sine and side rule. That is to say, we found out that those two sides and the angle that is included between those two sides, this right triangle APQ is equal to those two sides and the angle that is included between those two sides in this green triangle, triangle BPQ. And therefore, those two right triangles can go to each other according to sine and side rule. Again, we have those two sides and the angle that is included and the angle that is included between those two sides in this right triangle is equal to those two sides and the angle that is included between those two sides in this rectangle. Therefore, those two right triangles can go to each other according to side and side rule. And for the fact that those two right triangles can go to each other, we will know that they have also the same areas. That is to say, the area of the right triangle APQ equals to the area of the green triangle PBQ. But again, from the fact that those two right triangles are going to each other, we will have that they have also the same areas. That is to say, the area of the right triangle APQ equals to the area of the green triangle PBQ. So if we define the area of this green triangle as A, that is to say, the area of this green triangle PBQ equals to H coincident side according to our definition, then the area of this right triangle APQ must be also equal to H coincident side because they are equal to each other in their sizes. And the second thing that we have that from the fact that those two right triangles can go to each other, we have that their corresponding sides must be also equal to each other and their lengths. That is to say AQ equals to BQ. Side AQ of the right triangle equals to side BQ of the green triangle according to the rule that says that corresponding sides and right triangles are equal to each other. Those two triangles can go to each other, therefore their corresponding sides must also equal to each other and then next. That is to say AQ equals to BQ. So here we square this equation 2. So we get that AQ square equals to BQ square. We can implement the product theorem on our drawing. According to the product theorem, in any right triangle, the square of the hypotenuse equals to the sum of the slopes of the perpendiculars. So, we will implement the product theorem on this right triangle APQ. According to the product theorem, on this right triangle APQ, AQ square equals to AP square plus BQ square. Again, according to the product theorem, on this right triangle APQ, AQ square equals to AP square plus BQ square. So AQ square equals to AP square plus Q square. AQ square equals to AP square plus plus PQ square. Therefore, we can substitute AQ square by AP square plus PQ square. we are talking about this white hydride ADQ. This white hydride ADQ, according to the Balanced AQ squared, that is the square of the hypotenuse, equals to AD squared plus DQ squared. And AQ squared equals to AD squared plus DQ squared. Therefore, we can solve AQ squared by AD squared plus DQ squared. And again, according to the Balanced law, on the white ADQ, AQ squared equals to AD squared plus DQ squared. And it is AQ squared equals to BQ squared. We have BQ squared. So if we focus on the right rectangle BQC, we get that BQ squared equals to BC squared plus CQ squared. Again, BQ squared equals to BC squared plus CQ squared. Therefore, we can substitute BQ squared by BC squared plus CQ squared. And again, because of the fact that in this rectangle BCQ, BQ squared equals to BC squared plus CQ squared, we substitute BQ squared in this equation 2 by BC squared plus CQ squared. So in total, according to equation 2, we found out that AD squared plus DQ squared equals to BC squared plus CQ squared. AD is 9, therefore d squared is 9 squared, that is 81, plus DQ squared. DQ, we define DQ as x. What is the value of QC? QC equals to DC minus DQ. Again, QC equals to DC minus DQ. So, write it down. QC equals to DC minus DQ. So QC in total equals to DC. DC is 8 according to our definition, according to what is going to the question, minus DQ. DQ is x according to our definition. So in total, we found out that QC equals to 8 minus x units in its name. This is the missing side QC. This is equals to 8 minus x units in its name. So in total, we found out that dq squared equals to x squared. So we substitute dq squared in equation 2 by x squared. AD squared is 81, dq squared is x squared. In the other side of the equation, for equation 2, we have equals to bc squared plus cq squared. BC is 7, therefore BC squared is 7 squared, this is 49. Plus CQ squared. CQ is 8 minus x, therefore CQ squared is 8 minus x squared. So in total, according to the equation 2, we found out that 81 plus x squared equals to 49 plus 8 minus x squared. So 81 plus x squared equals to 49 plus 8 minus x squared. So we find out the value of 8 minus x squared according to the algebraic identity that says that a minus b squared equals to a squared plus b squared minus 2 times a times, again, a minus b squared equals to a squared plus b squared minus 2 times a times b. So according to the algebraic identity that I mentioned, 8 minus x squared equals to 8 squared, that is 64, plus x squared minus 2 times 8 times x, that is minus 16x. Here we have x squared on both sides of this equation, so x squared gets cancelled. After cancel x squared, in this side of equation 2 we left only with 81, while on the other side of equation 2 we have 49 plus 64 is 113 on 16x. So total according to equation 2, we found out that 81 equals to 113 on 16x. Here we add 16x to this equation 2. 16x minus 16x is 0, so here 16x will get cancelled. So in this side of equation 2 we have left only 113, while on the other side of equation 2 we have 81 plus 16x. So So today according to equation 2, we should now know that 81 plus 16x equals to 113. Here we subtract 81 from this equation, equation 2. And if I get it according to equation 2, 81 also 81 is also, here we have 20 with 16x. This side of equation 2, and on the other side of equation 2, we have 113 minus 81 is 32. So in total, according to equation 2, we know that 16x equals to 32. Here we divide this equation 2 by 16. And when we get according to equation 2, x equals to 32 over 16 is 2. So x equals to 2 units in its there. dq equals to x and x equals to 2, that is to say dq equals to 2. As you know, qc equals to 8 minus 6. 8 minus 6 is 8 minus 2, that is 6. So today we shall know that dq equals to 2 units in its name and qc equals to 6 units in its name. Those two angles are both defined as one-sided interrogants. Again, those two right angles are both defined as one-sided interrogants. The sum of those two one-sided interrogants is of course equals to 180 degrees. Therefore, according to rule 20, because of the fact that the sum of those two one-sided interrogants is equal to 180 degrees, they must be located between parallel lines. That is to say, side AD is parallel to opposite side BC, according to rule 20. So, application of rule 20, according to rule 20, if the sum of two interior one-sided angles is equal to 180 degrees, then they must be located between parallel lines. In the drawing, we have line A, this is line B, this is the red transversal C that cuts those two lines, A and B, and those 2 points. Those two angles, alpha and beta, they are both defined as one-sided interangles. So if alpha plus beta equals to 180 degrees, then they must be located between parallel lines. That is to say, line A is parallel to line B. According to this rule, rule 20. Likewise, those two angles are gamma and delta, and they are both defined as one-sided interangles. So if gamma plus delta equals to 180 degrees, then they must be located between parallel lines. Then line A is parallel to line B. We only implemented rule 20 in our drawing. When I put our drawing, as I already mentioned before, the sum of those two one-sided interangles is equal to 180 degrees. Therefore, they must be located between parallel lines. That is to say, AD is parallel to BC. So in total, we found out that in the big quadrilateral ABCD, side AD is parallel to side BC. That is to say, the big quadrilateral ABCD has one pair of parallel sides. It is parallel to BC. Therefore, the big quadrilateral ABCD is a trapezoid. On the fact that a trapezoid is defined as a quadrilateral with one pair of parallel sides. So to tell I know that quadrilateral ABCD is a trapezoid. Because it has one pair of parallel sides. But what is the area of trapezoid ABCD? This is trapezoid ABCD. Trapezoid ABCD, side AB is parallel to side CD. Those two parallel sides are defined as the bases of the trapezoid. So if side AB equals to A and side CD equals to B, then the area of this trapezoid ABCD must be equal to the sum of those two parallel sides, that is to say it is A plus B times the height edge over 2. Okay. The area of this trapezoid ABCD equals to the sum of its two parallel sides, that is to say it is A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. And the height edge creates 90 degrees with this base CD. Likewise, that H plus 90 with this base AB. So in total, the area of trapezoid ABCD must be equal to the sum of its two parallel sides. In this case, it's A plus B times the height H over 2. And the height H must create 90 degrees of those two parallel sides. We can use the new formula in order to find out the area of this trapezoid ABCD. According to the new formula, the area of trapezoid ABCD is equal to the sum of its two parallel sides, that are the two bases. That is to say, it is AD plus BC times the height. The height must get 90 degrees with the two parallel bases. Again, the height must get 90 degrees with the two parallel bases. CD definitely creates 90 degrees with the base AD, and also creates 90 degrees with the base BC. Therefore, the height is CD over 2. So in total, we found out that the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is to say, it is AD plus BC times the height CD over 2. And again, according to the first method of calculation, the area of the big trapezoid ABCD equals to the sum of its two parallel bases, that is AD plus BC times the height CD over 2. AD is 9 plus BC is 7 times the height DC is 8 over 2. So in total, we found out that the area of this big trapezoid ABCD equals to 9 plus 7 times 8 over 2. 9 plus 7 is 16. If we have 8 over 2 is 4, so in total this expression equals to 16 plus 4, that is 64. So according to the first method of calculation, we found out that the area of the big trapezoid ABCD is equal to 64 square sides. Actually, we have another way to find out the area of this big trapezoid ABCD. It is very clear that the area of trapezoid ABCD must be equal to the sum of the areas of the four components that it consists of. That is to say, the area of this big trapezoid ABCD must be equal to the area of the first component that it consists of, plus the area of the second component, plus the area of the third component, plus the area of the fourth component that trapezoid ABCD consists of. So according to the first method and to the second method of calculation, they have the same big trapezoid ABCD. Equal to the sum of the areas of the four components that it consists of. The first component is the right triangle ADC. They have the ADQ. They have this triangle ADQ. They have this right triangle ADQ equals to the base that is 2 times the height that is 9 over 2. 9 times 2 over 2 is 9. So there the first component that the ABCD consists of is equal to 9 squared in size. Plus the area of the second component that trapezoid ABCD consists of. The second component that trapezoid ABCD consists of is the right triangle APQ. And according to the definition, the area of the right triangle APQ is equal to A squared in size. So the area of the second component is A squared units. Likewise, the area of this third component is also A, because of the fact that those two triangles can go into each other, they have also the same area. So the area of the fourth component is also A squared in size, plus the area of this fourth component. The area of this what is the fourth component is actually the green triangle BQC or BCQ. The area of the green triangle BCQ equals to the base QC, that is 6, times the height CQ, that is 7 over 2. So it is 6 times 7 over 2. 6 times 7 is 42. 42 over 2 is 21. So in total, if you want to know that the area of this fourth component that the ABCD consists of is equal to 21 square units in size. So the area of the big trapezoid must be equal to 9 plus 8 plus 8 plus 21. And again, according to the second method of calculation, the area of the same trapezoid ABCD equals to 9 plus 8 plus 8 plus 21. 9 plus 21 is 30, 8 plus 8 is 2a. So according to the second method of calculation, we have found out that they are the same trapezoid ABCD is equal to 30 plus 2a squared in its size. This is according to the second method of calculation. But according to the first method of calculation, we have found out that they are the same trapezoid ABCD is equal to 64 squared in size. So we have two different equations. They have the same trapezoid ABCD. Equation 1 and equation 2. Therefore, we get the equation 3 that says that they have the big trapezoid ABCD according to the first method of calculation must be equal to the area of the same trapezoid ABCD according to the second method of calculation. Very simple equation. The area of trapezoid ABCD according to the first method of calculation equals to 64 squared in size. It must be equal to the area of the same trapezoid ABCD according to the second method of calculation. The area of trapezoid ABCD according to the second method of calculation equals to 30 plus 2a squared in size. So in total, according to equation 3, we have found out that 6 equals to 30 plus 2a. So we will subtract 30 from this equation, equation 3. So here 30 will get cancelled, and left only 2a in this side of this equation 3. While on the other side of equation 3, we have 64 minus 30 is 34. So in total, we found out that according to equation 3, 34 equals to 2a. Here we will divide this equation 3 by 2, and we get that a equals to 34 over 2 is 17. A equals to 17 square units in size. So now the right side AP2 is A. So and A equals to 17 square units in size. That is to say the area of the right side AP2 is equal to 17 square units inside. Likewise, the area of the right triangle BQ also equals to A, and A equals to 17 square units in size. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it's very easy to see that the area of this green shape equals to the area of the right triangle PBQ plus the area of the right triangle BQC. The area of the right triangle PBQ is A, and A is 17, and the area of this right triangle BQC is equal to 21 square units in size. So in total, the area of the green shape is equal to 17 plus 21. 17 plus 21 is 38 square units in size. So in total, if you want to know that the area that we are looking for this question, that is the area of this green shape, is equal to 38 square units in size. So finish to answer the second question. In the next step, answer the lecture. That is to say, we repeat on the solution of the first question, and then we repeat on the solution of this second question. In the first question, our test is to find out the radius of this circle. So in the drawing, we have quadrilateral ABCD that is described by this circle. Side AD of quadrilateral ABCD equals to 6 units in itself, side AB equals to 4 units in itself, side BC equals to 4 units in itself, and finally side DC equals to 5 units in itself. Again, our test is to find out the radius of this circle. So first of all, we define this angle BCD as alpha, therefore the opposite angle must be equal to 180 degrees minus alpha according to rule 22. Repeat quickly on rule 22. According to rule 22, the sum of two opposite angles in a cyclic quadrilateral is equal to 180 degrees. Quadrilateral in BCD is of course a cyclic quadrilateral. Therefore, the sum of those two opposite angles must be equal to 180 degrees. This is to say A plus B equals to 180 degrees. Likewise, the sum of those two opposite angles must be also equal to 180 degrees. That is to say X plus Y equals to 180 degrees. We only implemented rule 22 in our drawing because of the fact that in this cyclic quadrilateral ABCD, the sum of those two opposite angles must be equal to 180 degrees. So if this is angle alpha, then this means the angle must be equal to 180 degrees minus alpha. Because 180 degrees minus alpha plus alpha is equal to 180 degrees. It is the sum of those two opposite angles inside the cyclic quadrilateral ABCD. Therefore, this means the angle must be equal to 180 degrees minus alpha. According to rule 22. The next step, we join points B and D together by side line. By joining points B and D, we divided quadrilateral ABCD into two parts. The first part is the green triangle ABD, and the second part is the lower triangle ABCD. So the next step, we implemented the law of cosines for both triangles. So the green triangle ABD, and on the lower triangle BDC. So repeat quickly on the law of cosines. The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. This is angle BAC. This equals to theta degrees inside. Angle BAC equals to theta degrees inside. Side AB, this triangle ABC equals to 1 unit in itself. Side AC equals to B units in itself. And finally side BC equals to 3 units in itself. So in this triangle ABC, that could be any triangle, according to the law of cosines, the following equation is to C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So in the first step, we implemented the law of cosines. So this green triangle ABD. According to the law of cosines, in this green triangle ABD, the following equation is to BD squared equals to AD squared plus AB squared minus 2 times AD times AB times cosine 180 degrees minus alpha. Okay, again, according to the law of cosines, this is triangle ABD. The following equation is to BD squared equals to AD squared plus AB squared minus 2 times AD times AB times cosine 180 degrees minus alpha. Equation 1 is the implementation of the law of cosines on this triangle ABD. We have the trigonometric identity that says that cosine 180 degrees minus alpha equals to minus cosine alpha. Get cosine 180 degrees minus alpha equals to minus cosine alpha. Therefore, we can substitute cosine 180 degrees minus alpha in equation 1 but minus cosine alpha. Okay. It is true according to this trigonometric identity. So in total, we found out that BD squared equals to AD squared. AD is 6, therefore AD squared is 6 squared, that is 36. Plus AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. So again, in total, we found out that AD squared equals to 36, AB squared equals to 9. Minus 2 times AD, that is 6, times AB, that is 3. Times cosine 180 degrees minus alpha. And according to this trigonometric identity, cosine 180 degrees minus alpha equals to minus cosine alpha. So in total, we found out that BD squared equals to 36 plus 9, that is 45. In this given expression, minus times minus is plus. So this given expression in total is a positive expression, so it is plus 2 times 6 is 12, 12 times 3 is 36. So in total, the value of this positive expression is plus 36 times cosine alpha. So in total, according to equation 1, we found out that BD square equals to 36 plus sine is 45 plus 36 times cosine alpha. In the next step, we implemented the law of cosines. This lower triangle BDC. According to the law of cosines, in this lower triangle BDC, the following equation is 2. BD square equals to DC square plus BC square minus 2 times DC times BC times cosine alpha. But again, this lower triangle BDC, according to the law of cosines, the following equation is 2. BD square equals to DC square minus DC square plus BC square minus 2 times DC times BC times cosine alpha. Again, equation 2 is the implementation of the law of cosines of this lower triangle BDC. BD is the missing side, so we leave it as it is, so it is BD square equals to DC square. DC is 5, therefore this C square is 5 squared, that is 25, plus BC square. BC is 4, therefore BC square is 4 squared, it is 16. And DC square is 25, BC square is 16, plus 2 times DC, that is 5, times BC, that is 4, times cosine alpha. So this expression equals to minus 2 times 5 is minus 10, and minus 10 times 4 is minus 40, so this expression equals to minus 40 times cosine alpha, and 25 plus 16 is 41. So in total, if you found out that according to equation 2, BD square equals to 41 minus 40 times cosine alpha. This is according to equation 2, and according to equation 1, we only found out that BD square equals to 45 plus 36 cosine alpha. So we have two different equations for BD square, equation 1 and equation 2. Therefore, we can do the equation 3 that says that BD square according to equation 1 must be equal to BD square according to equation 2. Very simple equation. BD square according to equation 1 equals to 45 plus 36 times cosine alpha. It must be equal to BD square according to equation 2. BD square according to equation 2 equals to 41 minus 40 times cosine alpha. So total according to equation 3, we should find out that 45 plus 36 times cosine alpha equals to 41 minus 40 times cosine alpha. So here we subtract 41 from this equation 3, so here 41 we get cancelled, and therefore only we find 40 times cosine alpha on this side of the equation 3, while on the other side of the equation 3 we have 45 minus 41 is 4, plus 36 times cosine alpha. So in total, according to equation 3, we found out that 4 plus 36 times cosine alpha equals to minus 40 times cosine alpha. So here we did 40 times cosine alpha to this equation 3. 40 times cosine alpha minus 40 times cosine alpha equals to 0. And on this side of the equation we have 4 and 40 times cosine alpha plus 36 cosine alpha equals to 76 cosine alpha. So the total according to the equation 3, we found out that 4 plus 76 times cosine alpha equals to 0. Here we subtracted 4 from this equation 3, so here 4 again cancelled, and we left only with 76 times cosine alpha. And on the other side of the equation 3, we have 0 minus 4 is minus 4. So in total, according to equation 3, we should find out that 76 times cosine alpha equals to minus 4. So here we divided this equation, we divided this equation 3 by 76. So in total, we should find out that cosine alpha equals to minus 4 over 76. We would like to find out the value of alpha itself. In order to find out the value of alpha itself in this equation 3, we must operate the inverse function of cosine on the result of cosine alpha, that is minus 4 over 76. In this way, we get the value of alpha itself. We find out in any simple scientific calculator that the inverse cosine on minus 4 over 76 equals to 93.017 degrees. Those two sides of the equation are equal to each other. That is to say, alpha equals to 93.017 degrees. So if you found out that this is again alpha, this equals to 93.017 degrees. What is the value of BD? So we found out that according to equation 2, BD square equals to 41 minus 40 times cosine alpha. So BD square equals to 41 minus 40 times cosine alpha, and alpha is 93.107 degrees. The total according to question 2, if you found out that BD squared equals to 41, once 40 times cosine alpha. This expression in the green color, that is to say, once 40 times cosine 93.017 degrees is equal to 2.105. So in total, this expression, according to question 2, if you found out that BD squared equals to 41, and the value of this expression is 2.105. So total according to question 2, if you found out that BD squared equals to 41 plus 205. So BD squared equals to 41 plus 205 is 43.105. So in total according to question 2, if you found out that BD squared equals to 43.105. Here we took out of this equation and equation 2, if we found out that BD equals to the square root of 43.105, that is actually 6.565 units in Islam. Again, total BD equals to 6.565 units in Islam. In the next step, we implemented the law of sines in its full version on the lower triangle BDC. First of all, the lower triangle BDC is definitely inscribed by this circle. Why the lower triangle BDC is inscribed by this circle? Because of the fact that all the three vertices of this lower triangle BDC, that is to say vertex D, vertex B, and vertex C, are located on the circle itself. Therefore, triangle BDC is definitely inscribed by this circle. For that reason, we can implement the law of sines in its full version on this lower triangle BDC. So please click on the law of sines. This is triangle ABC that could be a triangle. This is angle BAC, that is equal to capital A degrees in size. This is angle ACB, that is equal to capital C degrees in size. And finally, this is angle ABC, that is equal to capital B degrees in size. Likewise, side AB, this angle ABC equals to 3 units in itself. Side AC equals to B units in itself. Finally, side BC equals to A units in itself. In addition, triangle ABC is inscribed by this circle. On this circle blocks triangle ABC. The radius of this circle is R. So, in our drawing, according to the law of sines in its full version, the following equation is 2. A over sin 3 equals to B over sin 3 equals to C over sin 3 equals to 2R. Again, A over sin 3 equals to B over sin 3 equals to C over sin 3 equals to 2R. So, you can implement the law of sines in its full version on the lower triangle BDC because of the fact that the lower triangle BDC is inscribed by this circle. So according to the law of sines in its full version, we get that BD of sin alpha equals to 2R. Again, BD of sin alpha equals to 2R, and now is the radius of this circle. This blocks triangle BDC, or triangle BDC inscribed by this circle. And R is also the radius that we are looking for in this question. So according to the law of sines in its full version, if you implement the law of sines in its full version of the lower triangle BDC, we get that BD of sin alpha equals to 2R. BD equals to 6.56 and alpha is 93.017. So total, again, BD is 6.56 and alpha 93.017 degrees. So in total, if you found out that 6.565 over sums 93.017 degrees equals to 2R. The value of this expression in the green color, in total this is equal to 6.5745. So those two sides of the equation are equal to each other. So in total, we found out that 6.5745 equals to 2R. If we divide this equation by 2, we know that R equals to 3.287 units. So the radius of this circle, that is the radius that we are looking for in this question, is equal to 3.287 units in its length. So finish to repeat on the first solution of the first question. The next step, repeat on the solution of the second question. In the second question, our test was to find out the area of this V shape. So in the drawing, we have the big quadrilateral ABCD. Those three angles are all right angles. Side AP, line segment AP equals to side line segment PB. Side AD of this quadrilateral ABCD equals to 9 units in itself. Side DC equals to 8 units in itself. And finally, side BC equals to 7 units in itself. Again, our test was to find out the area of this V shape. So first of all, AB is one side of one, the other ABCD, therefore it is absolute straight line. So if you focus on the lower side of the straight line AB at point B, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line AB at point B? We have this angle, this is right angle, plus this missing angle, and total the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore this missing angle must be equal to 90 degrees inside. And again, total if you don't know this is the missing angle, that must be equal to 90 degrees inside according to Rule 3. In the next step, we join points N and Q together by side line, and join points B and Q together by side line. By doing those constructions, we get those two right angles. This is the white right angle PQ, this is the white and the green right angle PBQ. So in the next step, we prove that those two right angles can go into each other according to side angle side rule. Why those two right angles can go into each other? First of all, AP equals to PB according to what is going in the question. In addition, those two angles are both right angles, and therefore they are equal to each other. And for this side, PQ is a common side that belongs to both angles, so we can write out that PQ equals to itself is a common side that belongs to both angles. So total, we all know that those two right angles can go into each other according to side angle side rule. Again, total, if you know that the white right angle APQ can went, this is the sum can went, to the green right angle PBQ according to side angle side rule. That is to say, if you found out in total, that those two sides and the angle that is included between those two sides in this white right angle APQ was more equal to those two sides and the angle that is included between those two sides in this green right angle BPQ. Therefore, those two right angles can go into each other according to side angle side rule. But again, we have those two sides and the angle that is included between those two sides in this right angle because we equal to those two sides and the angle that is included between those two sides in this green angle. Therefore, those two right angles can go into each other according to side angle side rule. And from the fact that those two right angles can go into each other, first of all, we know that they are also the same areas. Why? Because of the fact that any two triangles that can go into each other, they must have also the same areas. So if the area of this right angle PBQ is Z, then the area of this right angle PQA must also equal to A. Why? Because they have the same areas. So in the next step, the second thing that we concluded from the fact that those two right angles can go into each other, therefore their corresponding sides must also equal to each other and their lengths. That is to say, AQ, the right angle, must be equal to the corresponding side QB of the rectangle. YAQ is the corresponding side of QP, YAQ is the corresponding side of QB, because of the fact that those two sides are both the opposites of those two right angles. Therefore, they are definitely the corresponding sides. So the second thing that we concluded is that AQ equals to BQ. Again, AQ equals to BQ according to the rule that corresponding sides and right angles are equal to each other. Those two right angles can go to each other, therefore they are corresponding sides, that is to say AQ must be equal to BQ. So here we square this equation too, and finally found out that AQ squared equals to BQ squared. Here you can implement the product theorem. This white right angle ADQ, according to the product theorem, in any right angle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So in the white right angle ADQ, AQ square equals to AD square plus DQ square. Again, AQ square, that is the square of the hypotenuse, equals to AD square plus DQ square. That is to say, if we can substitute AQ square by AD square plus DQ square. Again, according to the product theorem, AQ square equals to AD square plus DQ square. Therefore, we substitute AQ square by AD square plus DQ square. This is all according to the product theorem. And AQ square equals to BQ square. BQ is the hypotenuse of the rectangle BQC. According to the product theorem, this rectangle BQC, BQ square equals to BC square plus CQ square. Therefore, we can substitute BQ square by BC square plus CQ square. This is all according to the product theorem. And substitute BQ square by BC square plus CQ square. So total according to the equation, we found out that AD square plus DQ square equals to BC square plus CQ square. AD is 9, therefore d squared is 9 squared, that is 81. We define the length of dq as x. So if dq is x, it means that dq squared equals to x squared. And again, AD squared is 81, dq squared is x squared. What is the value of QC? QC equals to DC minus DQ. QC equals to DC minus DQ. DC is 8, DQ is x. And QC equals to 8 minus x. So in the other side of question 2, we have in total BC square plus CQ square. BC is 7, therefore BC square is 7 squared, that is 49. Plus CQ square. CQ is 8 minus x, therefore CQ square is 8 minus x square. So in total question 2, if you want to know that 81 plus x square equals to 49 plus 8 minus x square. Repeat again. Total if you want to know that AD square plus DQ square equals to BC square plus CQ square. AD square is 81, DQ square is x square, and it equals to BC square plus CQ square. BC is 7, therefore BC square is 7 squared, that is 49. Plus CQ square. CQ is 8 minus x, therefore CQ square is 8 minus x square. So in total according to equation 2, if you want to know that 81 plus x squared equals to 49 plus 8 minus x squared. So 81 plus x squared equals to 41 plus 8 minus x squared. 8 minus x squared equals to 8 squared, that is 64, plus x squared minus 2 times 8 times x, that is minus 16x. So here we have x squared on both sides of the equation, so x squared will get cancelled. X squared will get cancelled, so x squared, and this is side of the equation we have to leave 81. And on the other side of the equation 2, we have 49 plus 64 is 113 minus 16x. So in total according to the equation 2, we should now know that 81 equals to 113 minus 16x. So here we added 16x to this equation 2. 16x plus 16x is 0, so in this of the equation 2 we have only 113. On the other side of the equation 2 we have 81 plus 16x. So in total, according to equation 2, I can know that 81 plus 16x equals to 113. Here we subtract 81 from this equation 2. And in this side of the equation 81 we get cancelled, we have only 16x. But on the other side of this equation 2 we have 113 minus 81 is 32. So in total we should find out that 16x equals to 32. Here we divide this equation 2 by 16, and we found out that x equals to 32 over 16 is 2. So x equals to 2, and therefore here we have 8 minus x is 8 minus 2, that is 6. QC equals to 6, DQ equals to 2. Those triangles are both defined one-sided triangles. The sum of those one-sided triangles is of course 180 degrees. Therefore, according to Rule 20, they must be located between parallel lines. That is to say, AD is parallel to BC according to Rule 20. So specification on Rule 20. According to Rule 20, if the sum of two one-sided triangles is equal to 180 degrees, then they must be located between parallel lines. In the drawing, we have line A. This is line A, this is line B. This is the transversal C that cuts those two lines, A and B, and those 2 points. Those triangles, alpha and beta, they are both defined as one-sided triangles. So if alpha plus beta equals to 180 degrees, then they must be located between parallel lines. That is to say, line A. Then line A is parallel to line B. Likewise, those triangles, the gamma and delta, they are both defined as one-sided triangles. So if gamma plus delta equals to 180 degrees, then they must be located between parallel lines. Then line A is parallel to line B. So actually, we only implemented all 20 in our domain. Because in our domain, the sum of those two one-sided triangles is of course equals to 180 degrees. Therefore, they must be located between parallel lines. That is to say, AD is parallel to BC. So in the big quadrilateral ABCD, we have one pair of parallel lines, parallel sides, that is to say, side AD is parallel to side BC. Therefore, quadrilateral ABCD is defined as a trapezoid. Because the definition of a trapezoid is quadrilateral with one pair of parallel sides. And so if you know that quadrilateral ABCD is a trapezoid, because it has one pair of parallel sides. But what is the area of trapezoid? This is trapezoid ABCD. AB is parallel to CD. The length of AB is A. CD equals to B since length. Those two parallel sides are defined as the bases of the trapezoid. The base AB equals to A. The base CD equals to B since length. So the area of this trapezoid ABCD equals to the sum of its two parallel bases, this is to say it is A plus B times the height edge over 2. The height edge must get integrated with the two parallel sides. You see, each gets integrated with the base AB and each gets integrated with the base CD. So total the area of this trapezoid ABCD equals to the sum of its two parallel sides, that is to say it is A plus B times the height edge over 2. So we can find out the area of this trapezoid ABCD according to the formula. The area of trapezoid ABCD must be equal to the sum of those two parallel sides times the height over 2. That is to say, it is AD plus BC. The height is DC. Why the height is DC? Because it's 90 degrees with the base AD, and the height DC also 90 degrees with the base BC. Therefore, this is the height. So in total, the area of trapezoid ABCD equals to the sum of its two parallel sides, that is to say it is AD plus BC times the height DC over 2. And again, total the area of this trapezoid ABCD equals to the sum of its two parallel sides, that is to say it is AD plus BC times the height CD over 2. AD is 9 plus BC is 7 times DC is 8 over 2. And again, AD is 9 BC7, CD is 8 over 2. 9 plus 7 is 16, 8 over 2 is 4. So total its expression equals to 16 plus 4, that is 64. So according to the first method of calculation, we actually found out that the area of this big trapezoid ABCD is equal to 64 squares in size. But we have another way to find out the area of this trapezoid ABCD. The area of the big trapezoid ABCD must be equal to the sum of the areas of the four components that this consists of. That is to say, the area of the big trapezoid ABCD must be equal to the area of the first component the trapezoid ABCD consists of, plus the area of the second component the trapezoid ABCD consists of, plus the area of the third component the trapezoid ABCD consists of, plus the area of this fourth component the trapezoid ABCD consists of. So next we calculated the area of each component separately and then the four areas together. The first component is the area of this right triangle ADQ. The area of the right triangle ADQ equals to the base 2, to base the DQ, that is 2, times the 8AD, that is 9 over 2. 9 times 2 over 2 is 9, so the area of the first component is 9 squares inside. The area of the second component that the trapezoid consists of is equal to 8 squares inside according to our definition. Likewise, the area of the first component is also equal to 8 squares inside, because of the fact that those two areas can go into each other, must have also the same areas. Thus, the first fourth component that the trapezoid ABCD consists of. The fourth component is the right triangle BCQ. The of this right triangle BC equals to the base CQ, that is 6, times the height CB, that is 7 over 2. 6 times 7 is 42, and 42 over 2 is 21. So they have the four components that the ABCD consists of is 21 squares in size. So total, the area of the big trapezoid ABCD equals to the sum of the areas of those four components. That is to say, it is 9 plus A plus A plus 21. 9 plus 21 is 30, A plus A is 2A. So total, the area of the big trapezoid ABCD is equal to 30 plus 2A squares in size. This is according to the second method of calculation, but according to the first method of calculation, we already found out that the area of the big trapezoid ABCD equals to 64 squares in size. So we have two different equations for the area of the same trapezoid ABCD. Equation 1 and equation 2. Therefore, we have equation 3 that says that the area of trapezoid ABCD according to the first method of calculation must be equal to the area of the same trapezoid ABCD according to the second method of calculation. Very simple equation. So the area of trapezoid ABCD according to the first method of calculation equals to 64 squares in size. It says it must be equal to the area of the same trapezoid ABCD according to the second method of calculation equals to 30 plus 2A. So total according to equation 3, we found out that 60 equals to 30 plus 2A. So here we subtract 30 from this equation 3. So here 30 we get cancelled, and in this side of equation 3 we have left only 2A. While on the other side of the equation 3 we have 64 plus 30 is 34. So total according to equation 3, we found out that 34 equals to 2A. Here we divide this equation 3 by 2. So we found out that A equals to 34 over 2, that is 17. A equals to 17 squares in size. So they have this right triangle APQ is A, and A equals to 17 squares in size. Likewise, the area of this right triangle BBQ also equals to 17 squares in size. And the area of this right triangle BBQ equals to 21 squares in size. Our task is to find out the area of this region. It is very clear that the region equals to the sum of the areas of those two right triangles. It is actually 17 plus 21, that is 38 squares in size. And again, total the region equals to the area of the two right triangles. It is actually 17 plus 21, that is 38 squares in size. So total, if you want to know that the area that we are looking for in this region, that is the area of this region equals to 38 squares in size. Okay, thank you very much.